Hello and welcome to my talk about unraveling time, understanding time formats in iOS, Sysdiagnose for security forensics. And well, first of all, why is this all important? Well, probably you all fly here somehow and probably also got some like time format changes or in general like system time changes. And well, we will uncover how actually Sysdiagnose is going to save this and also like probably also in what time formats it saves things. So the importance of time in Sysdiagnose is basically, well, of course, if you want to investigate an incident probably because someone tampered with your system, then you want actually to know which changes in files you had. And of course, for this, we need the time to be exact, to pinpoint when a compromise happened. And you want to probably also know how the compromise happened, and therefore time is very nice. But first of all, like, how do we actually do a Sysdiagnose? Basically, you just press 3 buttons, the volume up, volume down, and the power button. Then the system or the iPhone vibrates and gives you a signal that actually a Sysdiagnose is being created. It roughly takes about 5 to 10 minutes. And then we can see in our settings under privacy and security, down in the analytics and improvements section, that there are probably analytics data, for example here, this is Sysdiagnose. And well, if you've opened a Sysdiagnose file, you probably mentioned some directories and also some files, and with some I mean a lot. Even the logs directory, for example, is very full and has a lot of directories, which also contains directories and entries. So I'm going to show you some examples, like what you actually can find. So this one is the BDC .csv file, which sometimes contains cycle counts and, for example, also the charging voltage. Then we have the mobile activation D log file, which looks like this. And also we do have the log daemon 0 log, for example, which looks like this. But as you may noticed, the files actually didn't look the same. And interesting, I'm in a loop now. Files do not have a common format, but how about the time formats, for example? Well, of course, we have to look into time formats now. So I'm showing you some, quite common formats for this. So this is like the offset to UTC zone, which kind of looks like this. So we have the date, the time, and then sometimes with a plus or minus, which indicates in which time zone you are. Also, sometimes we see the UTC before the plus or minus. Then there is also a common format known as ISO 8601, which just has the date and the time, and actually the Z behind it says Zulu, which is actually a military term for Greenwich Mean Time. Then, of course, we have the Unix epoch. You may have seen it around also in Unix file systems. It's just a 10-digit number in seconds. Then, of course, we also have the RFC 3339, which kind of looks like ISO, but has a tiny separator instead of the space, or sometimes an underscore. We see a T here, and also a more precise one with milliseconds. And we also see some time abbreviations, just like the date, the time, and then the time zone. And yeah, if we translate it to, for example, a time, then it looks somewhat like this. So I'm showing you some example files actually, which are used in Sysdiagnose. So for example, here we have the log daemon helper 0 log, and we can see right in front that we have a time And this, of course, is a offset to UTC because it uses the plus and then the indicator. Then we have the ISO 8601, which also in front of we see the time zone. And as I said, sometimes the time of ISO is displayed with an underscore, sometimes with a space. Then for an example, for the RFC 3339, we have actually here in the Unified Asset Manager log this timestamp, which actually indicates with a T and also with a Z that we are in the UTZ zone. Then the Unix epoch, for example, here in the calendar time of the ASP snapshot log, we can see a 10-digit, and it's also indicating calendar time, so maybe it's a time. But there are actually even more, not like the common formats. So we've seen, or I've seen in mobile activation D-log 0, that the time format is actually a complete different one. So we have also the weekday and the month, then the day, then the hours, and then the year. So very odd. Then, but also we could find, for example, in the stacks.ips file, that there are also multiple formats used in just one file. For example, here in the top, we can see that the timestamp actually is a kind of UTC offset. But if we look down further, in the kernel description, we also see another new format for us. But there is also more. So in the hit util plist, which is a very long file, there are several contained. For example, here we have the RFC version. We have also a UTC offset, and we have also a Unix file, a Unix time. And also at the bottom, we also see a new one occurring. And well, I've plotted some data actually, and it's quite rough. So under other, there are, I think, like 10 more like combinations or also single ones, which are actually very, very odd. But actually, most of the time, formats used in Sysdiagnose is actually ISO 8601. And then after that, there is the ISO and Unix combination, which is used most. But the question is now, like, how does our time change actually? And therefore, we just think about like flying, for example, from Germany to Ireland. And in Germany, my phone is connected to a cell tower. And if we then fly actually to Ireland, then we're gonna connect to a new cell tower. And also our system time gets updated because we are crossing a time zone. In this case, for example, from 1421 to 1321. There's actually an event triggering the time change, which is also logged in the log daemon 0 log, which is called time zone change updating file headers. And we can also see when this happens. In this case, it's just 1 hour apart. But sometimes log daemon is not that like precise, and I've also seen in my research that there are also times which are 10 hours apart, sometimes days apart, so you can never be certain about when actually this event got triggered. So we can look into the hit util plist again. And we can see here, for example, that we are also crossing a time zone again. So in this case, we have about like 3 minutes of preciseness, but can we get even more precise? So for example, in the app conduit, we can find that there are actually like about 2 or 1.5 minutes away. In the log data statistics 0 log, we can even find that they're just 1 minute away. And those are actually concurrent entries. And then we have the log daemon helper log, and this actually is also roughly about like 8 minutes apart. But yeah, can we get more precise? And the answer is yes. Again, the hit util plist helps here. And we can uncover that we're just 10 seconds apart. And also we can see here that there is also start time since epoch entry. And the key also does change just 10 seconds. But can we get even more precision? And the answer is yes. If you enable the baseband logging, which is a logging you have to enable for debugging purposes, but it also gets expired in 21 days, so you have to do it manually very often. You can actually see here that we have multiple loggings per second, and also can see directly when time changes. In this case, we have an odd 1 hour jump, but in most cases, or in general, baseband logs like multiple times a second. So probably here was a time shift. So to conclude, how could you detect time changes? Well, the most precise one is actually the baseband log, if possible, but the most info you actually get through the hit util-p list, the system log archive, especially the log daemon logs and the log data statistics log. But there are also some kind of useful in app conduit and mobile activation logs. And mahalo also to Andy and Patrick for inviting me, and mahalo to you. And yeah, thanks, that was my talk.